This video is on Unit 3 on radical equations, Chapter 7, rational exponents and radical equations, lesson number 1, radicals and roots. In the very beginning of your notes here, under warm-up, it says list the perfect squares, cubes, and fourths. So we already know what perfect squares are. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. So that list of numbers there on that line for perfect squares are all of them up to 10. And of course, it keeps going. So we know our perfect squares. The next line is your perfect cubes. So 1 times 1 times 1 is still 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27, and so on. 64 is a perfect cube. 125 is a perfect cube. 216. And again, I've got that up through 729, and it continues on. And then you've got your perfect fourths. 1, again, is a perfect everything. If you'll notice, 1 starts every single list. 2 to the 4th power is 16. 3 to the 4th power is 81. 4 to the 4th power is 256, and so on. So there's your beginning of your long list of perfect fourths. In this lesson, one of the things that we're going to focus on is simplifying radicals that have a different index. Parts of a radical. The nth root of a real number a can be written as the radical expression nth root of a, where n is your index. A is called the radicand, so that's the number that's under the radical symbol. And then, of course, you've got your radical sign itself. If there is no index, it is assumed that n equals 2. Now, we've talked about that already. If there is no index listed, it's called a square root. So there's an understood 2 there. Otherwise, if you see something other than, a number there, it's going to indicate something other than a square root. In this first part of our examples, it says number of roots. It says give all possible roots to the radicals below. So when we ask for the square root of 16, think back to when we were solving square roots. The square root of 16 could potentially be a positive 4 or a negative 4. 121 could be 11 or negative 11. 289 could be a positive or a negative 17. And then the square root of 4/25 could be a positive or negative 2/5. Now, I will say this. Unless it's indicated, typically when you see a square root symbol, like you see here in these examples, typically we're only looking for the principal square root, which is called the positive square root. It's called the principal square root. Okay? Typically. We'll talk more about that here in just a second. The next line is your cubes. The cube root of 8 is going to be a 2. Now, this cannot be negative. The thing about odd indices is there's only going to be one answer. If there's an even index, like a square root or a fourth root, we can have multiple roots. The cube root of 243, if you put it in the calculator, let me show you that real quick. Cube root is under math. So if you go to math, we're going to be using number 4 and number 5 occasionally. So if you select number 5, it gives you the opportunity to change the index to whatever you want it to, and then I'm going to put in the 343 so you can see that it's equal to 7. So this is equal to 7, and again, it can only be a positive 7. Number 3 says the cube root of negative 125. Now, don't confuse this with square root of a negative. So if we have square root of a negative, say 25, that's going to be a 5i. The square root of negative 1 is equal to I. Cube root is completely different. So if you think about a number times itself 3 times, that gives me negative 125, that's going to be negative 5, because negative 5 times negative 5 times negative 5 will give you negative 125. Again, this occurs when the index is odd. On the last one in that line, I've got the cube root of negative 1 over 27, which is going to be negative 1 over 3. The next line is our fourth roots. And again, the index here is even. Just like the first row, we can have multiple roots. I want the fourth root of 1. Well, 1 times 1 times 1 times 1 is 1. Negative 1 times negative 1 times negative 1 times negative 1 is also a 1. So this can be a positive and a negative 1. On the fourth root of 2,401, the fourth root of 2,401, it can be a positive or a negative 7. And I want to show you here again, math. I'm going to select number 5, fourth root of 2,401, we get 7. So I want to show you something else. If I take 7 and I raise it to the fourth power, I should get that 2401. Same thing with the negative 7 raised to the fourth power. I still get the same positive 2401. So the fourth root of 2,401 can be a positive or a negative 7. The fourth root of 4,096 can be a positive or a negative 8. And then the fourth root of 81 over 16 is going to be a positive or a negative 3/2. So this next little table is kind of a way to put into words what we just discovered in those examples. So if you've got an even index and a positive radicand, so even index, so that's like the first line or the third line, an even index, but the number underneath is positive, what types of roots do you have? Well, we have real roots. They're going to be real, not imaginary, real. And how many can we have? The number of roots, because you can have a positive or a negative, right? We might have 2 roots. What if our index is odd? So that would be that middle row. If we're looking at that middle row, if the number that's inside is positive, what are the types of roots here? Well, they're still real. They're still going to be real. And how many can we have? Well, there's only going to be one answer there. And I've said that as we were going through that. There's only going to be one. If the number underneath is positive, then it's only going to be positive. Versus odd index but negative. If the number underneath was negative, it's still a real solution, a real answer, a real root. But the answer is going to be negative. And again, there can only be one of those, just a negative answer. The last one has a star beside it. For even and negative, the types of roots here are going to be imaginary. And again, you can have 2 of those because one can be positive and one can be negative. All right, so right here, it says if a radical has more than one root, the radical sign indicates only the principal or positive root. So again, typically, if we're taking, say, the fourth root of 1, that's asking for the principal square root, which is 1. If we were solving an equation and we were looking for all the potential possible answers, there might be an answer that could be a negative 1. But usually we're just looking for the principal or positive root. So let's look at simplifying these square roots or cube roots or fourth roots or fifth roots. Again, depending on what that index is. So number 1 and 2, we've already done some like these. I'm gonna go through one more time and show you a quick way to simplify this. If I'm trying to simplify the square root of 117, you are either going to look for the perfect square that is a factor, which I can tell you is going to be 9, 117 is going to break down into 9 times 13. And then you take the square root of 9 and you get 3 radical 13. Or you're using the calculator. Y equal 117 divided by x squared. And I can go to my table of ordered pairs and find that same answer, 3 radical 13. 3 square root of 13. On number 2, there is a number in front. So if I'm finding the square root of 320, y equals 320 divided by x squared. I'm going to get 8 square root of 5. 8. So I got 4 times 8 times the square root of 5, which gives me 32 times the square root of 5. Again, I know there are some of you that are using the perfect squares, which is great. I'm just using the calculator for those that are using the calculator. Number 3, we've got 2 times the cube root of 48. So this is a little different. If I'm looking for the cube root, I'll forget the 2 for right now. I'm going to just go ahead and put him out to the side. If I'm looking for the cube root of 48, those of you who are doing this mentally, you're now trying to figure out, is there a perfect cube that is a factor of 48? And you got to go back to that list of perfect cubes. And this is where it gets harder to do this in your head because we don't know our perfect cubes like we know our perfect squares. So is 8 a perfect cube that's a factor? Is 27 a perfect cube that's a factor? Is 64 a perfect cube a factor? So inside of 48, I can tell you that there is a perfect cube, and it's 8. 8 times 6 is 48. And the cube root of 8 is 2. And then I have got my cube root of 6. You can't really see my 3 there. It's a 3. And 2 times 2 is 4 times the cube root of 6. That's my little index is kind of hard to read. Still can't read it. You know it's a 3. If you're going to use the calculator, so those of you that have gotten used to using that calculator function, I want to show you how this is going to look. So we've got to take 48 divided by x. Because this is a cube root, we're going to raise this to the third power. So we want 48 divided by x cubed instead of x squared because it is a cube root. Now when I go to the table, I'm still going to get the 2 cube root of 6, just like we did a minute ago. And then you multiply the outside number times the 2 that was already out there. Let's do that again. So number 4, I've got 3 times whatever I get when I simplify the cube root of 108. So I'm going to go to the calculator. 108 divided by x to the third power. And we get 3 cube root of 4. And then don't forget to multiply your 3 times the 3 to get your 9 cube root of 4. Those of you that are looking for the perfect cubes, it would be a 27 times 4. So you would have broken 108 down into 27 times 4 to get the cube root of 108 to be the 3 cube root of 4. Now let's keep going. In example number 5 and 6, what you should notice on the inside is that we've got negatives, but the index is 3. So a negative on the inside just means there's going to be a negative on the outside. Again, if there is a negative on the inside of an odd index, you're going to have a negative on the outside of the radical. So for cube root of negative 250. Cube root of negative 250. If you're doing this mentally, the perfect cube that is a factor of 250 is going to be the 125. It would be a 125. You got negative 1 times 125 times 2. And again, the cube root of negative 1 is negative 1. So I would have a negative 1 on the outside. Cube root of 125 is 5 and then that 2 is going to stay under the radical. If you're using the calculator, I would go to y equal, again, just do the 125. You're going to know that the negative underneath an odd index is going to be a negative on the outside, so I would not make that a negative. I should have made that 250. So sorry. Y'all are probably screaming at me. So there's your 5 cube root of 2. And again, it's going to be negative 5 because there's a negative on the inside and it is a cubic root. On number 6, 2 is prime. So the only thing that we can do to this is bring the negative that's on the inside outside. So this one's just going to be negative 6 times the cube root of 2. Number 7, I've got 3 times the 4th root of 162. So here again, those of you that are trying to do this mentally, this is where it starts getting more and more difficult, is I'm trying to find now all the perfect fourths that are a factor of 162. So then I've got to go back to this list of perfect fourths and start dividing those out. So looking at 162, what's going to be a factor of 162 is going to be the 81. The 81 that is a perfect fourth is going to be a factor. So 81 times 2, 4th root of 81 is going to be 3. And then we end up with 9 times the 4th root of 2 for our final answer. Those of you that are using the calculator, again, because it's the 4th root, when you put in the 162 divided by x, you're going to raise that x to the 4th power because the index is 4. Second graph, and there's your 3 and your 2. So you end up with the same answer. Let's look at number 8. 5 times the 4th root of 2,592. I'm going to leave the 5, and I'm going to do this in the calculator. 2,592 divided by x to the 4th power is going to give me a 6 times the 4th root of 2. So 6 times the 4th root of 2, and I get 30 times the 4th root of 2 for that answer. All right, the next section is on radicals with variables. So when we're dealing with square roots, exponents must be multiples of 2. Cube roots, exponents must be a multiple of 3. And for 4th roots, your exponents must be a multiple of 4. So when we look at example number 9, we've got the square root of 32 x to the 4th y to the 9th power. The index is a 2. Okay, so we're doing square root of 32. 32 is going to be 16 times 2. Again, if you're using the calculator, you're going to go to y equal 32 divided by x squared. So the square root of 16 is 4, and then the 2 is going to stay underneath. Now let's talk about our variables. So here's how, there's a lot of different ways to explain this, but here's how I do it. When I look at x, it has an exponent of 4. The understood index here is a 2. So if I take 4 and I divide that by 2, I get 2. So that means there's an x squared on the outside of that radical. But y to the 9th power is a little different. If I take 9 and I try to divide by 2, that does not go evenly. Well, how many of those y's would divide evenly? Well, that would be 8 of them, right? If I take 8 of the 9 and I divide by 2, I get 4. So y to the 4th power is going to be outside. And how many did we have left over? There was just 1 left over. So the answer on number 9 is 4x squared y to the 4th times the square root of 2y. Well, let's look at another one of those. Another square root, number 10. I've got the square root of 324, a to the 3rd, b to the 7th. Again, the index is 2. So the square root of 324, if you want to do this in the calculator, we can. Y equals 324 divided by x squared. And I get, oh, it's a perfect square. 324 is a perfect square. It's 18. Okay. I didn't know that one. So the square root of 324 is 18. Okay? Now let's look at the a's. A to the third power. If I have an index of 2, how many a's can come outside? Well, if I've got 3 and I want to try to divide that by 2, that's not going to work. It doesn't go evenly. But 2 of them would. So if I had 2 divided by 2, that gives me an a on the outside with 1 left over. So the leftovers are always going to stay inside the radical. And then b to the 7th, if I try to take 7 to divide by 2, that's not going to work. But what if I take 6 of them? That goes evenly. So 6 divided by 2 is 3, with that 1 left over b that's going to have to stay on the inside. So your answer to number 10 is 18 ab cubed times the square root of ab. All right, let's do an example of a cube root, a couple of cube roots, and a couple of fourth roots. Number 11 has got the cube root of 216 m to the third n to the sixth. So now my index is 3. And when we start dealing with those exponents on the variables, we need the 3, not a 2. So we're looking for the cube root of 216, which the cube root of 216, I think is actually 6. No, it's 8. The cube root, cube root of 216, I'm pretty sure is perfect. The cube root of 216. Oh, it's 6. Just kidding. It's 6. It's 6. So 6. Now, what about my m to the third? Well, 3 divided by my index of 3 gives me 1 on the outside. For my n's, 6 divided by 3 is going to go even. That's going to be a 2. And so I have n squared. There's not going to be anything left on the inside of that radical. So my answer for number 11 is just 6mn squared. Number 13. Let's jump down to number 13. So here again, you have an odd index with a negative under the radical. That means you have a negative on the outside because the cube root of -1 is -1. And then the cube root of 64 is going to be 4. So for my number part, I've got a -4 on the outside of my radical. Because again, the cube root of 64 is 4. Cube root of -1 is -1. So -4. How about my x's? So 10 divided by 3. Well, that's not going to work. 3 doesn't divide into 10 evenly. But 3 divides into 9 of them. So 9 divided by 3 is 3. So I'll have x to the third power on the outside. And there was that 1 left over x that's going to stay under the radical. Y to the 21st power, 21 divided by 3 goes evenly. And it's a 7. So I'll have y to the 7th. And then my radical, the only thing underneath my radical is that x. So the answer for number 13, I don't like how that looks, will be a -4 x to the third y to the 7th times the cube root of x. Number 15, the index is 4. Actually, let me do number 16. Number 16, the index is 4. I have the fourth root of 48, m to the 8th, n to the 3rd. So the fourth root of 48. So is there a perfect fourth power that is a factor of 48? Well, yes. It would be 16 times 3. And the fourth root of 16 is going to be a 2. And then the 3 is going to stay underneath that radical. Now, let's talk about the variables. So I have m to the 8th. So 8 divided by 4 will go evenly. I'm going to have m squared on the outside. And then n to the 3rd, when I try to take 3 divided by 4, not only does that not go evenly, there's not enough n's to have an n come outside. So the n to the 3rd is going to stay under. So your answer here is 2m squared times the 4th root of 3n to the 3rd. On number 17, I've got the 4th root of 625, c to the 3rd, d to the 11th. So I'm looking for the 4th root of 625. I feel like that was on the list. It was. 625 is a perfect 4th power. It's 5. So I have a 5 in the front. For your C's, if you think about 23 divided by 4, again, that's not going to go evenly. But how many of those 23 would divide evenly by 4? Well, 20 of them would, right? 20 of the 23 will divide by 4 evenly, giving us an exponent of 5. So that's going to be c to the 5th power. How many did not divide evenly? 3 of them. So c to the 3rd is going to stay underneath. 11 on the D, 11 divided by 4. Again, that's not going to go evenly. But how many of the 11 would divide evenly by 4? 8 of them. 8 divided by 4 is a 2, leaving me with 3, d to the 3rd on the inside. So the answer on number 17 is 5, c to the 5th, d squared, I forgot my index, times the 4th root of c cubed, d cubed. I do want to quickly talk about 18. It looks complicated, but it is not. If you think of your y plus 3 as a single entity, the y plus 3 is being raised to the 8th power. So how many times will 4 divide into 8 evenly? Well, that'll be 2. So technically, this just becomes y plus 3 squared. And of course, you could FOIL that out. Y plus 3 times y plus 3. And you get y squared plus 3y plus 3y plus 9, giving us y squared plus 6y plus 9 for our final answer on number 18. So there are your notes for Unit 3, Chapter 7, Lesson number 1 on radicals and roots.